ladies and gentlemen, class recording has started. So, in yesterday's lab, we took a look at the properties of a couple of different compounds. And what we're going to do today is hopefully make sense of why those compounds, because of what they're made up of and how the atoms are bonded together, have the properties that you observed in yesterday's lab. But first thing, before we get into that, there's a part at the top of your outline that it wasn't part of the PowerPoint, but is important to our understanding. And that part looks like this. So at the top of your outline, there are three pictures, right? And those three pictures are representing what?
Gases, liquids, and solids.
Gases, liquids, and solids, or more generally, our states of matter, right? So, back in 6th grade or back in 7th grade or whatever, you probably learned a little bit about states of matter, right? So what are some of the general properties that we learned about when dealing with solids, liquids, and gases? Elise, what's one thing?
They have to have space, weight, and take up space.
What does? Oh, that means matter in general, right? Okay, so those are our definition of matter. Let's talk more about, like, specifically. Nicole, yes?
Gases and liquids take the shape of their container.
Okay, so gases and liquids both have no definite shape, right? That, Nicole, like you said, they will take whatever the shape of whatever container they are in, okay? Which is contrary to solids, right? Solids have a definite shape, and it will not change regardless of what container you put it in. All right, so that's one characteristic. What else? What else did you learn about solids, liquids, and gases back in 6th, 7th grade? Farah, what else?
Solids have a definite volume.
Okay, solids will have a definite volume. They will take up the same amount of space. Okay, what else? Let's finish this off here. Farah, go ahead.
Liquids have a definite volume.
Liquids still have a definite volume as well. They take up the same amount of space. What that space looks like changes depending on the container, but they still take up the same amount of space. But as far as a gas is concerned, right, what do gases do?
No definite volume.
No definite volume, right? Gases will fill up whatever container we put them in. Case in point, at least twice a week, somebody sprays Axe body spray in the hallway, okay?
I have some in my
But
bag.
then,
It's
please
dry.
don't spray it in here, okay? But then soon, now you don't just smell it by their locker, right? Now you smell it through the entire hallway because gases will take the shape of whatever container they're in. They will completely fill it up. They have no definite shape and no definite volume. Okay, good. Now let's talk about the particles that make up these three things. What do we know about the particles or the molecules or the atoms that make up our different states of matter? Sir?
Gases and molecules are spread apart.
Okay, gases, particles are real far apart. Particles are far apart. And what else do you know about the molecules of a gas? Barb?
They're moving really fast.
They move really fast. Okay. Which is obviously different than, let's say, the molecules that make up a solid, right? What do you know about the molecules of a solid?
They're
Go
very
ahead.
densely packed.
Okay, they're very densely packed. So particles very close. Okay? How about not just close? Very close, right? And what else do we know about them? How about their movement? Sir?
They're moving slowly.
They're moving slowly.
Very.
Specifically, what are they doing? Do we remember what they're doing? They kind of like,
Jiggle.
they like jiggle or shake or vibrate. I'm just doing that because that's what Becca was doing. I don't know if you guys can see that or not, but you know. All right. So as far as their movement goes, right? They vibrate.
Oh, yeah.
Okay. And then we can sort of make, that comparison to liquids as well. How close together are liquid particles going to be?
Close, but not very.
Close, but not real close. How much are they allowed to move?
Title of a band of our story.
Can liquid particles move from one side of this glass of water to the other side?
No.
Yeah. They have that ability to sort of move in and out and slide past one another, but not really the ability just to fly off into the room. right? Is that good? Good. Glad we got that sound effect in there too. That's important. All right, I'll add this. I'll add that in post production.
What are we writing?
Not really. All right, are we good on these properties?
Yes.
Okay. These properties are important because it relates to what we see about these different substances that are put together with different bonds. So as we learned yesterday, the physical properties of a substance are affected by the attractive forces that exist between the particles. Okay? The greater the attractive forces that exist between the particles, the more energy is required to overcome those attractive forces. Meaning, if we want to make the particles of a gas move, how much energy do we have to put in? Not a whole lot. Are gas particles attracted to one another?
No.
Not very much. Why not? They're really far apart, and what else do they do?
They move fast.
They move really fast. So they're really not attracted to each other at all. But if we want to make the particles of a solid move faster, that's a lot harder, right? Because why?
They're closer together.
They're real close together, and do they move a whole lot? No. So they're very attracted to one another, okay? Relatively speaking. Does that make sense?
Yeah.
Okay. So let's talk first about the first kind of bond that we talked about, okay? Like ionics, okay? Let's go here. All right. Here is, not that one, this one. Here is an atom of sodium, okay? And then here is an atom of chlorine, okay? We've discussed on numerous occasions what's going to happen here, right?
Bang.
What's going to happen here? What's sodium looking to do? Lose one electron. What's chlorine looking to do? Gain one. So we're going to have that transfer of electron. Sodium's now going to become this, and now it's what?
Sodium chloride.
Not yet. What is sodium?
Okay. It's
What-
an
Sodium is a cation now. So it has a positive charge. I'm going to group these together. Okay? And now, chlorine has what? Chlorine has that negative charge, right? It is now a what? Anion. It's grouped together. And now that sodium has a positive charge and it's cation, chlorine has a negative charge and it's an anion, what's going to happen? Right? They attract each other like this. Okay? But just because sodium with its positive charge is now attracted to chlorine with its negative charge, does that mean sodium has lost its positive charge? No. Still positive, it's just attracted to that negative one. So, let's say another chlorine comes along. Okay? Is this positive sodium going to be attracted to this negative chlorine? Yeah. Even though it's already attracted to this negative chlorine, that doesn't mean it lost its positive charge. It's still positively charged, it's still attracted to negative things. So, this chlorine is going to line itself up kind of like this. Right? But does this chlorine come by itself?
No.
What was it already attached to? It's already attached to another sodium. So now it's going to line itself up kind of like this. Does that make sense? Okay? Guess what? Another chlorine comes in like this, but what does this chlorine come with? Another sodium, right? And then guess what? Now there's a positive sodium that comes over here and it's attracted to this chlorine, right? But what does that positive sodium come with? A negative chlorine.
This is getting crazy.
Okay, so now you got this picture. And if I just showed you this picture at the beginning, could you really tell which sodium lost its electron to which chlorine? Not if I just showed you this picture, and this is a really incomplete picture, right? Because what we find out is that in ionic solids, in ionic compounds, the way they arrange themselves, it's not just one positive attached to one negative. We get this nice little pattern. Positive, negative, positive, negative, positive, negative, positive, negative. And it doesn't just happen sideways. It happens up and down, like I'm showing you here, right? But it also happens like coming out of the board and going into the board. And we call that nice, regular pattern of positives and negatives a three-dimensional network called a crystal, or a crystal lattice. Okay? That each ion, whether it's positive or whether it's negative, is attracted to multiple ions of the opposite charge. It's not just one for one positive, one negative, okay? But because of that, right? Actually, here, let me get this. If you're writing stuff down, I apologize. I'm really just going to try and move a little bit quicker today, okay? So if you haven't written it all down, it's online. You can get it. Okay? So, as far as that goes, we refer to these as interionic forces. Because you know English, you probably could tell me about interionic forces. What does the prefix inter mean? Not inside. Between. Right? So, inter means between, and ionic means ions, right? Between ion forces. Interionic forces are due to the attraction of oppositely charged ions. There is a greater attraction the greater the charge there is. So there is a strong attraction between the +1 on the sodium and the -1 on the chlorine. But there is a stronger attraction between the +2 of magnesium and -2 of oxygen. The bigger the charge, the stronger they attract one another. These are the strongest kind of forces that exist out there holding particles together. If these are the strongest kinds of forces, how much do you think these individual ions have the freedom to move? How close do you think they are together? So what state of matter are most ionic compounds going to exist in? Solids. Okay? That leads us to the properties of ionic compounds. Ionic compounds have really high melting points and really high boiling points, meaning most of them are solids at room temperature. Most ionic compounds will dissolve in water. What happens is that those individual positive and negatives will actually start to separate because of what water does to it. That's important because once you get those separate positive and negative charges, that allows current to flow. If there's a voltage difference, blah, 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 blah. All those things we learned last unit. Okay? But in the solid form, ionic compounds aren't very good conductors because can those charges move through that crystal structure? Because why? They're all held tight together. Those forces are too strong to allow anything to move really very far. Okay? Good as far as ionic compounds are concerned. Is that good? Okay, now, let's talk a little bit. I'm going to skip over one part of your outline. Okay? And let's go underneath Roman numeral 3. Let's skip right down to nonpolar covalent bonds. So, we learned about nonpolar covalent bonds earlier in this unit, right? What can you tell me about a nonpolar covalent bond? What's something that we remember about nonpolars? Katie?
They share the electrons evenly.
They share electrons nice and evenly, okay? Meaning that they have a similar what, Katie?
Similar electronegativity.
They have similar electronegativities. That means, though, that if we look at their electron clouds, right, are we going to see a distribution of a bigger cloud on one side versus the other side? No. Nice even distribution. And that means there's no separation of charge. A nice even distribution. Okay? Is that good? Which is different, right, than if there's a nice even distribution, all of these individual positive cations and negative anions. But if I were to draw a compound that was held together by nonpolar bonds, right, those two are bonded to each other, so there's a strong attraction between the two of them, but do they have any attraction for this over here? There's really no positive side on one to latch on to the negative side of the other one. There's really just not much interaction there. How hard is it to separate them? Not very hard at all. It's pretty easy, right? So what does that mean? What state of matter then they tend more towards? Liquids and even gases. Because if they don't attract each other, right, how hard is it to get them all separated like this?
Not very.
Not very hard at all. So, nonpolar covalent bonds have really low melting points and boiling points. A lot of them are gases at room temperature. This room is filled up with what? Oxygen is one thing, but also, what else is what is most of air made out of?
Nitrogen.
Nitrogen, okay? If you remember from earlier, nitrogen and oxygen are both diatomic molecules. Does that sound familiar? Okay. What did, who asked me? You asked me, right? What did you learn? Sarah. You.
Oh, me? Okay.
What did you learn about diatomic molecule from taking your quiz?
They're non-polar.
They are nonpolar because there's no separation of charge there. They each want those electrons just as much as the other one. So they don't attract each other very much. They also don't conduct electricity, no matter whether they're dissolved in something or not dissolved or anything. Okay? They will dissolve in certain things, certain substances, but only substances that, if it's nonpolar covalent, they'll dissolve in other nonpolar covalent things. Okay? Good there. Go ahead, Farm.
When you were showing us the picture, and you said that it's not hard to take them apart, did you mean the one,
No.
the one molecule, or you mean like if all four were?
Good question. Okay? Alright. These two are bonded together. They're a group. It's hard to separate these two because, like we said, the nucleus here is attracted to the electrons over here, right? And then the nucleus here is attracted to the electrons over here. These two are hard to separate, but they are easy to get away from these two that are joined together. These have no attraction for these, okay? But these two are very strongly attracted to each other. This is a covalent bond. This is what we refer to as an intermolecular force, because it's the force between molecules. Nonpolar covalents have very low intermolecular forces, meaning they are very easy to separate. Okay? Is that good?
So, two non-polar covalent molecules, they still will, like, they still will attach, but if they do, it's easy to separate.
Right, yeah. There is some attraction there, but it's very small. But very easy to separate, which is a good transition. I'm glad you went this way with the whole intermolecular force, okay? Because the next thing we talk about is polar covalent bond, right? So, generally speaking, what do we know about polar covalent bonds? Matt, go ahead.
The electron negativity, different between them, so one has a greater attraction for electrons than the other one.
Good.
So they're positive and negative.
There is a greater attraction for electrons between one of those atoms than the other atom, right? One wants electrons more than the other one. And that means they're not going to share those electrons equally. So, what does it end up looking like? It ends up looking ends up looking like this, right? What did we say the cloud represented? Where the electrons are likely to be found, right? And that means in this molecule, we're going to find electrons more on the left-hand side than the right-hand side. Does that make sense? That's a polar bond. But more important to that is that if we're finding a bunch of electrons over here on the left-hand side, what does this side of the molecule start looking like or start becoming?
Negative.
It becomes not negative like an anion, right? But negative like air quotes, right? Okay? So we start getting this side being negative. And if that side's going to be negative, what's going to happen on the other side? It's going to be positive.
Quote unquote positive.
Not positive positive, but air quotes positive. Okay? Does that make sense?
Yes.
Alright, so next thing I do, I draw your attention to the two pictures that are at the bottom of page 2 of your outline, especially this one. Okay? So, we have these blue eggs, and inside these blue eggs are the little positive sign and the little negative sign. These blue eggs represent polar covalent bonded molecules. How do I know that these blue eggs represent polar covalent bonded molecules? Far, go ahead.
The arrows show that the positive sides are attracted to the negative side.
Okay, so we're seeing some attractions here, okay? But, Far, let me zoom in on this, okay? How do I know, oh, technology, I hope this works.
Oh, it's so cool. Oh.
Far, how do I know that this is a polar covalent bonded molecule? Patty, go ahead.
The electron cloud is like bigger around the negative side than the positive.
The electron cloud is bigger around the negative side than it is around the positive side. But, and that's true, but more important, how do I distinguish this? How do I know this isn't ionic? How do I know I'm not representing something that's bonded ionically? Elise.
Because they're like joined together.
Ah, they're both part of the same egg, right? If it was ionic, it would look like this, right? That's supposed to be negative, and this is supposed to be positive, right? And this is supposed to be negative. That's ionic, because there's a separate positive and a separate negative, right? Is that okay? But here, that positive and negative are all part of the same thing, same molecule. That's why this blue egg represents a polar covalent bond. But now, Far, the jump you made, right? If this side of the molecule is positive, and if this side of this molecule is positive, and this side of this molecule is negative, what are they going to start doing to each other? They're going to start attracting each other. Is it as strong as these attractions up here? No. These, remember, we called inter-ionic forces, but I just told you that we call these what? Intermolecular forces. Molecular. There we go. Okay. Is that good so far? Okay. How strong are these intermolecular forces going to be compared to these intermolecular forces?
Stronger.
Yes. Say again? Which ones? These ones?
Yeah.
Okay. We said that, sorry, these are, I keep forgetting I'm talking, so like if I'm talking, you guys can see it, but they can't, you know. We said these are tightly attracted to one another, right? but is this group on the top tightly attracted to this group on the bottom? No. But now that I start doing this, right, is this group here attracted to that group there? Yes. Is it real strong? It's not real strong, because remember, this isn't positive, it's positive. And this isn't negative, it's negative, right? But there's still some attraction there. Does that make sense? How hard is it to separate those? It's not real hard, but harder than these, than the nonpolar ones. So what does that do? We refer to these as dipole forces, where the negative side of one, quote unquote negative, and the positive side, quote unquote positive, of one molecule are attracted to another molecule. Not as strong as the interionic forces, but stronger than the intermolecular forces that barely exist between nonpolars. Okay? Is that good there? Okay. Okay, hold on 1 second. Let me do this and then I'll do it, okay? So what does that do to properties? Well, polar molecules do attract each other slightly, whereas nonpolar molecules have essentially no attraction for one another. And that means that polar compounds will be a little bit harder to separate, and that means that they have a little bit higher melting points. Not as high as like ionic ones, but let's say, I don't know, something like water. The attraction between those molecules is strong enough to do what? At room temperature, what state of matter is water? It's a liquid. Are the forces strong enough to hold them in place like a solid? No, but they're strong enough to keep those water molecules from doing what? Going off into a gas. Does that make sense? Okay. Still no ability to conduct charges because there's not actually positive and negative charges. There's just kind ofs. Does that make sense? Okay. So now, if you start taking a look at the properties of the compounds from the lab that we did yesterday, you're going to start seeing that patterns start existing, similar to the descriptions that we talked about today. Good there? Okay. Sorry for the uncomfortable pause on the recording. I'm thinking if I should do more or if I should just stop right now.
Only got 5 minutes.
Oh, I know. Don't you worry. Now we
Good
have
afternoon, pardon the interruption, just a
Yes,
reminder,
stop.
juniors taking the practice SAT tomorrow will need to bring pencils and your calculator. The test begins promptly at 8 a.m. in room 109. That is juniors taking the practice SAT tomorrow morning here, 8 a.m. in
Yes.
room 109. I'll see you there.
Okay, so real quick before I stop this recording. On the calendar for tonight, there are some homework problems dealing with properties of ionic and covalent compounds. Based on what we discussed today, we should be able to answer those questions. Also the lab analysis questions that go along with it. Okay? Good job today, everybody.